Well, today we shall start the same design of slabs, and this is part 5 so far the design of slabs concerned, and we are doing that right now. We are doing design of 2A slabs. Let me see whether I can show you one problem. I don't know whether it is can you view it, but only thing that I would like to tell, this is your this initially long back, almost say 2 years back, I tried to make it in Java, okay, because my initial plan was to make it in the internet, but Java somehow the way it started and somehow possibly it is flopped and the way. So anyway, I have stopped, I have discontinued this project, but I had lot of things regarding this, that say your truss as well as beam as well as your say plane frame, all those things I made it in Java. But anyway, I just found this one, but right now I am trying to make this one in Visual C++, because I am now again going back to the old system, to that C only, and that standalone program. Instead of going to the internet, I think it is better to, internet is still not so grown up possibly, though with the graphics lot of things are there, but even then, so far the technical thing is concerned, possibly it is still in the infant stage. So anyway, so I am now developing this one as a dual project, that dead wind earthquake live load, that what I have told you in one of the lectures, and this is the part of the design under RCC. So what I am trying to do, the language, this language was really good, and we have so many classes like C++, that a lot of things we can make it. But anyway, so let us come to that. This is this particular applet, generally in Java we call it applet. It is for only 2A slabs, but one thing I have not considered here, that your deflection criteria, that time I have not considered, because I thought, okay, I shall make it only to show. So what happened here, we have interior panels. I think it is I don't know whether, can you recognize this one? Okay. Okay, so interior panels, then one shortage discontinuous. I have told 9 different cases. So interior panels, one shortage discontinuous, one long edge discontinuous, 2 adjacent edges discontinuous, 2 short edges discontinuous, 2 long edges discontinuous, 1 long edge continuous only, 1 short edge continuous only, and all 4 edges discontinuous. So we have 9 different cases as per your say table 26, as per table 26 of IS 456 2000. What I have done for all the cases, I have simply given the input for, I have made a table internally in this, that all the your say coefficients alpha x alpha y for LY by LX. So what is the input we want? We want that shorter span which will be in meter, that is a 4 meter here, you can change it. Longer span, that is 5 meter. Dead load, here I have to specify the dead load. I should specifically mention that it is a factored load, but anyway, this is actually factored load or design load. That means after calculation of dead load, you should have. My initial plan was to give you the rectangle only, and the corresponding you would say that one rectangle like this. What I am trying to make, say my initial plan was like this. It may be something like that, and I shall try to make it that one in Visual C++. If this is your rectangle, so what we can make, whether this edge is continuous or discontinuous. I need not specify that one, that whether which case, but even I can go, and this could be radio button. I am trying to make little bit say computer aided. So one of them, only one of them could be either continuous or discontinuous. Similarly, this one also, this one also, this one also. And we can specify the your say length and your say that LX and LY. So the your GUI, that interface may come this type of one instead of say like this, though it is not a bad one, but anyway, but here you have to specify that which is the case, but we can go little more further. So dead load here we can specify, and live load, but this one here all of them are design load. And LY by LX, so let us find out, let me just show you. So, an overall depth you have to specify, overall depth we can specify, which we can get it from the control of deflection, but anyway I will specify that overall depth. Then clear cover you can mention depending on the exposure condition. Then bar diameter, so we are having so many bar diameters. So, it started from 6, but since in slab we start from 8, so initial one 8. So, 8, 10, 12 like that I have given all the bar because it is a class. So, the bar diameter is a class. So, I am just giving this one here. So, automatically whatever I shall select, so that one will come here. Now, concrete grade, what are the different grades? I have taken M15, M20, M25, M30. In IS 45 because it was made on based on IS 456 1978, so that is why I have kept it M15, but anyway sometimes we require also. So, I would like to keep this M15 also. And what about the steel grade? Steel grade we are having Fe 250, 415, 500, and since we mainly use 415, that is why the default one 415. Sometimes we may check it for dead load only and also dead load and live load only. That means I can either go for, this is called radio button. So, either I can check this one or I can check this one. Now, what will happen here? Let us see, this is your case, let us say for dead load and live load, let us compute. So, if I compute that one, immediately these coefficients will be taken from that table, in our case table 26. So, immediately it will be taken from that table, and the span moment and support moments for shorter span and longer span will be computed. If I choose say one shortage discontinuous, let us compute once more. So, you see that all the values are changed. So, what we can do, taking care all of them, say let us say 2 long edges discontinuous, this particular one, and let us compute. So, I shall get immediately I shall get those values, and here you can say that there is no support moment here. That 0 means that in this case discontinuous, that means almost a simply supported case. So, we can take that. So, these values will be automatically taken and it is linearly interpolated, and we are getting an immediately span moment, all those things will be computed. And the moment of resistance also, taking care of all the values, it will be taken, and we can find out the what is the overall depth computed, that also we can find out. So, and finally I can provide the reinforcement, because we can have 4 different types of reinforcement: shorter span support reinforcement, shorter span span reinforcement, longer span that support reinforcement, and longer span span reinforcement. And so, we can get, I think there is something wrong here, 97, it should be something little more, because 8 mm to 110, so it will be little more. So, we can have that all the 4 cases, and automatically we can choose. So, we can take say all 4 edges discontinuous, let us see. So, increase depth, that means it is not sufficient, that means it is telling increase depth. So, I can increase the depth. Okay. So, I can increase the depth to 125, and now I can see that it is coming. So, like that we can check, because just it is very much handy. The initial plan was that it is very much handy. Initial plan was that it will come under, all of them will come under that one site, and we can go to that site and immediately anybody can just use this program. That was my intention. But anyway, then I have found there is some other problem that somehow it has not, then I am coming back to the your say standalone program. Okay. So, anyway, this is the thing and which will come under that dual project. So, all those things including the your say analysis as well as design, and I hope that before the design of earthquake resistant structures, reinforced concrete, that time when I shall take a separate module starting from the analysis to design, and that time I shall use everything under dual, and I shall find out whether I shall be able to get that good GUI. Then I shall show, otherwise I shall show only numerical values. Okay. But anyway, and what I mean to say that design is such that it is very, very interesting also. I really like this one, because there are so many constraints, and with those constraints, if you have to design a proper economic as well as safe design, and that is really a challenge. And we do check lot of work also, that regarding say your bridges, for checking bridges, bridge design analysis, also see your residential buildings or any project. So, like that we continue. But anyway, so now let us come back to the problem, that few things before starting one say your example problem. Let us start with the detailing. because last class I have not finished that part. So, detailing of reinforcement, that is very, very important. So, I shall just simply tell you very few things that which we should know. Let us say this is a beam slab cross section. And let us give a center line. Okay. And we have the length L1, and the other part we can specify like this, that is say your L2. There are this detailing is very, very another important aspect of your say structural design, that you can design it, you can provide the reinforcement, but the proper placement of your say reinforcement, that is very, very important. So, in the wrong side, particularly in cantilever, if you specify the reinforcement in the wrong side, because the reinforcement in the cantilever, that is at the top, not in the bottom, the main reinforcement, and this is a sometimes there is a failure immediately after say casting. So, casting, and when it is removed the shuttering, immediately it fails, immediately it breaks. So, that is a very, very common one, and it happens also. So, that is why this detailing of the reinforcement is very, very important, and it should be done carefully. There are two things. In the early days, they used to make say your reinforcement as if it is like say this, just I am not writing, but as if you have okay, I think we can make it in a separate page. What we do, say if this is your slab, what we can do, that we make a crank here, the bars, this type of thing, and we make it, and there is another cut piece bar which can go start from here to here. This bar is, if I start this bar, this is your one bar, bent up bars, the one we have already done it in the beam. The other one, it can be cut piece. That means if you see the bar, you will find out in the plan, this is the plan of a say slab. If we start say regarding this bar, if I take the bars which are at the bottom, those bars say let us take say that is firm line, solid line, and bars which are at the top, that we shall show it as a say dotted line. So, what about this bar? If we look from the top, then it will happen that we shall find out dotted certain portion, and then it will start firm. I mean to say this bar. This is the usual way of showing the bar. The other one, because it may not be sufficient. So, what we can do, we can specify the other bar say like this, it can go, and then again firm like that, but in between that say this spacing is not sufficient. Let us say this spacing is not sufficient, we have to specify a little more bars. In that case, what we do, that this is another bar, this is another bar, and what we do, we specify another bar like this. This cut piece we specify here like this, so that actually it should be, sorry, it should be dotted, please excuse me, it should be dotted. So, this bar should be instead of firm, because we are talking at the top one. So, this bar should be dotted, and similarly here also there another bar, it will be dotted, and this spacing whatever it has to be, that has to be specified, that whatever say maybe say for example 8 torr at the rate of maybe 200 center to center like that. So, those cut pieces are provided and few bars cranked. Nowadays what we do not go this type of thing, because after all it needs certain kind of, say, that detailing also, that you have to know that how many bars you have to crank, all those things. Nowadays what we do, we take two different one, that bottom bars in the bottom, top bars at the top. So, what we do, that we just simply make the cut pieces, that means here this bar it is bottom. So, if it is not required, I shall cut it here itself. So, I shall show you, it may go like this. So, say this is one bar in the bottom, the other bar we just simply cut it here, that is I am talking for the bottom. Similarly, another bar here, the other bar which is coming here, because we do not require at the bottom, we do not require that much of spacing. So, if we can provide, so here we can just curtail the bar. So, that is the idea. So, if we do it, now what about the top one? The top one we shall take it, the bars, simply the top bars will be the top bars here. What will happen to the top bars? The top bars here will be, say, we have started, so it will be dotted. The second one also will be dotted like that. These are all separate bars, and we follow this type of detailing nowadays. We do not go that crank, all those things we do not go nowadays, and that way it is easy also. The top bars having separate spacing, all those things. Otherwise, what you have to do for detailing, that since you are doing that alternate crank, so if it is a 250 millimeter, say, your spacing, so alternate crank, that means 125, all those things you have to make it. So, the spacing, all those things, it is dependent on the top bars also. Say for example, you are getting, say, 125 millimeter at the bottom, for example 125 millimeter bottom and 250 millimeter top. So, in that case I can specify that 125, that means the bottom we can have this type of thing. These are all 125 millimeter center to center, and the top alternate one we are making crank. So, that means then we can specify this one as 250. So, that means here, but if it is, say, something 130, 140, so alternate one it may not be, say, 240 or 280, that we cannot provide, it has to be restricted to, say, 250 maybe. So, that means your top and bottom bars, all of them are dependent. So, here in this case, when you are making that separate one, the detailing for the top as well as for the bottom, then there is no dependency, and so we can go separately for top bars as well as separately for the bottom bars, and that is the idea what we nowadays follow. So, now if we come back to the specific one, why I am telling this, that if we take this section, then where is that curtailment, that is that we have to mention. So, here what we do, what we can do it here, there are two types of thing. So, these bars whenever we are specifying, as well as here also one bar, number one, where from the bar will start, this bar if we take it, where from this bar will start, that is your first question. So, if the spacing, this is your, say, spacing, let us say this is S or P, pitch also we call it, P or S, and then what will happen, this one should not be greater than, let us say, either we can say P by 2 or S by 2. I mean to say this length, that is your P. So, that means it should not be greater than P by 2. So, that we should always, it will be within P by 2, that we shall start the bar, that is number one. Number 2, let us say this is your AS1, area of steel 1 of this one. Similarly, we can have the area of steel other also. If this is the area of steel which we are providing here, the length span is L1, what we shall do, what about the top bars? The top bars, this length, please note that from the end of the support, this length will be 0.1, this is the length L1, so it is L1, 10%. So, that length we have to specify. And what about the area of steel? This area of steel will be equal to half of the AS1. We are talking the end one, that 50% of the AS1, that area of steel, this one, the area of steel we are providing. So, 50% of that we have to provide here. Here we are supposed to get 0, but 50% of AS1 or 0.12%, that is the minimum steel we have to provide from the control of the crack width. So, that 0.12% of the cross sectional area, that we have to provide here, whichever is more, in that case we have to provide. And what about these 2 bars? These 2 bars, at least 2 or 3, whatever you provide, but at least there should be 2 bars, not 1 bar. We should have at least 2 bars. So, this is one case. Number 1, this is number 1 say. Number 2, in the middle, here in the support we do not need the span, whatever area of steel we have got it in the span, we do not need that much here, because after all here that span moment, here the moment is less at the bottom. So, we do not need that much. So, what we shall do it here, we can curtail the bar, maybe we can curtail the bar somewhere here, we can curtail the bar here, similarly we can curtail the bar here. These are the bars we are specifying here, that means we can say here 1 bar this length, the other bar will go, so that way alternate we can provide the bars. So, what about this length? That length will be equal to, where we shall curtail it, this one from the central line it comes 0.15 L1. So, it comes from 0.15 L1, but where from I am talking this? I am talking this all of them from SP 34 1987. This is the detailing of the reinforced concrete reinforcement. So, SP 34 is a special publication number 34 1987 by Indian standards. So, I am talking from that one. So, everybody has to follow this detailing. This length becomes 0.25 L1, and here what about this length? This length will be equal to 0.25, this is L2. So, this will be L2. So, one side it will be 0.25 L1, other side is 0.25 L2. So, because we are talking this span, so 25% of the length, and the other side also L2, this in the span is different, so it will be 25% of that. What about the top reinforcement? Top reinforcement can also have 2 different one, that means we can curtail it here itself, because we are not going that much. So, the 2 lengths, one is called this particular length we are getting from the end support 0.15 L1, and the other one it goes up to 0.3 L1. Similarly, this side 0.15 L2, and this length is 0.3 L2. What about the reinforcement? The reinforcement here, I am talking this one, this reinforcement, if I say AS2, area of steel on the support AS2, then this one will be 0.5 AS2. So, here we have a curtailment, because we know the moment also will reduce here. So, that is why you are not provide the full. So, 15% of the length this side, other side, here 15% of the length for this span, 15% of this span, that is the total AS2, and then 50% of that we shall provide here, and which is going up to say 0.3 L2 this side because the span is L2, and 0.3 L1 this side because the span is L1. So, we specify like this, we specify all the that you are detailing, that you have to, that curtailment of reinforcement, all those things you can do it. Otherwise, it will not be economic, and that you have to maintain it. Okay. This is one part. There are so many other things also, just I am giving you a few examples so that we can find out. The other example I can show you, that is your actually for corner reinforcement. Corner with two discontinuous edges. So, this is a corner of a slab. Let us provide the that support are dotted. Okay. So, what we can do it here, this one, if we start, so let us start here. The corner reinforcement you can provide, and the other side also. So, this is your that corner reinforcement we have to provide. Let us make it one more here like this. So, if we have this corner reinforcement, so what about your that length? This length will be equal to Lx by 5, the other one also from the end of the support face, this is also Lx by 5. What about the reinforcement? The reinforcement we are providing here, so this reinforcement, that one is coming as 3/4 of area of steel in the shorter span, whatever your area of steel you are getting in the shorter span moment due to shorter span moment. So, 3/4 of area of steel that you have to provide here, and that should be at the top and bottom both, that it should be at the top as well as in the bottom. Similarly, the other reinforcement, that we have to provide it also here, 3/4 AS area of steel, top and bottom. So, we are not directly computing that. So, what we are doing, since we know the span moment for longitudinal side as well as say shorter side as well as longer side, so shorter side one we shall take it, and 3/4 of that we shall provide it here, and that is why we write down top and bottom. Generally, what we do here for detailing, we mark those bars, that whenever we are having that one, it may be crowded. So, that is why what we do, we just simply provide say your this is say 1, this one we could say 2. So, now what we shall specify here 1, this is bar number, and maybe say we are providing something, say we can say 8 tor at the rate of maybe say 250 center to center, that we are providing. So, like that. Number 2 also here it may be say 8 tor at the rate of 250 center to center. If the spacing and your bar diameter same, then we can take it as the same type. So, that means I can just simply say this is 1 as well as this is also 1. So, that means we can reduce the number of bars. So, from the drawing itself they will come to know that how many different types of bar you need. So, that itself, and that is that you have to make it, that the list that you have to make it, that bar bending schedule also you can specify, that we make it separately in the right hand side of the drawing. So from there they will know that okay, this many number of bars, different types of bars we have to provide. LX is the span, that one we are talking. So LX LY, the one for the slab. So that is always in the shorter direction. When you are talking LX, so you mean to say that is in the shorter direction. So one more, I think I should make it. So the layout of corner steel so this one we can say corners with one discontinuous end. That means when we have only one discontinuous end, what will happen? So in that case, what we do? This is your say middle support. So this is your one beam, maybe this is also another beam. So here only one side is discontinuous. In that case, what we shall do? We shall provide the reinforcement here. So this is your reinforcement. Similarly, this side also. So let us extend it a little bit. So if we have this type of reinforcement here, then what about this length? This is again Lx by 5. What about this length? This one also you have to provide that Lx by also Lx by 5. And we provide the reinforcement this side, that one should be equal to 3/8 of area of steel, that's a span, that steel whatever we have got it, and that one will also will be at the top and bottom. What about the other one? The other one we also get the same one this side, and that also we take it 3/8 of area of steel, and that is top and bottom. So we have to provide that. So these are the corner reinforcement that we have to provide. So one is that totally the two discontinuous edges, and another one that only one discontinuous edges. So this is your that problem that we have to finish it. Until and unless you finish this detailing, then the work is not complete. That you have to specify. There are few other things also that I am not going to that, because otherwise it will be too boring. That maybe in the later stage I shall tell you that one. So let us just take at least one example problem for 2A slab with so many cases. Let us take just one case I am taking. Say I can write down this one as say A, B, C, D, E, F. These are the all column positions, and this side I can say 1, 2 and 3. This one say 5 meter, this one also say 5 meter, and this side we are having typical, I can say 4 meter. And we are interested for this panel, that is B1, C1, C2, B2. So this is your panel. Generally we specify in this fashion. So panel B1, C1, C2, B2, that is the panel that we have to design it. So what we shall do it here, we can say, shall I keep it for some time? You have copied this one. What we shall do this, that we would like to design this panel, and let us say that your live load 4 kilonewton per square meter. I can give the concrete grade, possibly concrete grade I have used M20 possibly. That concrete grade, that one we are using it here M20, and steel Fe415. So if we do this one, we have to design this, because out of that 9 cases we shall find out one of the cases, and we shall design according to the values given in table 26. So generally we can mention in this fashion. This is the continuous one, where this is 4 meter and this is 5 meter. So Lx equal to 4 meter and Ly equal to 5 meter. So we can take Ly by Lx equal to 5 by 4, which comes as 1.25. So we shall use table 26 to find out that values. We can use it, say, clear cover 15 millimeter, clear cover 15 millimeter for mild exposure. Let us take for your dead load calculation assume overall slab depth equal to 150 millimeter. We can check later on that whether we are getting the exact span by depth ratio or not. So here we are assuming say 150 millimeter. So then we shall find out the design load. So 150 millimeter is the overall slab depth, and so effective depth we can also calculate. Let us find out the effective depth. D equal to 150 minus 15. I can check again say 10 millimeter, maybe we shall get little less, but anyway we can take this one, and which is coming as say here, so 15 plus 130 millimeter. So D equal to that effective depth D, that is coming say 130 millimeter, because I am assuming 10 means the 10 torr. This is your 10 torr, we are assuming that we shall use it, but maybe later on we may use it 8 mm, 8 mm dia, but anyway. Number 2, design load. So dead load for slab, that is 0.15 into 1 into 25 equal to 3.75 kilonewton per square meter. Number 2, floor finish 0.025 if we take say 25 mm thick times equal to 0.6 kilonewton per square meter. Number 3, plastering, plaster say 6 mm thick. So this one you say 6 mm thick that we are using, so 0.006 times 24, that is equal to 0.144 kilonewton per square meter. So we can get the total dead load equals 4.494 kilonewton per square meter, and live load, that is 4 kilonewton per square meter. So design load equals 1.5 times 4.494 plus 1.5 times 4.0 equals 6.74. I think I should make it little bit clear. So 4.494 into 1.5, so 6.741 plus 6, which comes as 12.741 kilonewton per square meter. So this is your design load at which we have to take it. So design load we are getting 12.741 kilonewton per square meter. What about your type of slab? That is your type of slab according to your table 26. It is your, according to table 26, we are taking that shorter edge is discontinuous. So that is your actually in table 26, if you go, then you will find out that is your say case 2. So we can write down type of slab case 2, 1 short edge, other way also you can write down continuous also, and you will get it in table 26 IS 456 2000. LY by LX already you have computed, 5 by 4 equals 1.25. Now let us write down explicitly shorter span alpha x, and we have, that means it is between 1.2 and 1.3, that it should be LY by LX between 1.2 and 1.3, and we can have negative moment, that is at the support, and positive moment in the span, and the values comes 0.048. You can check it in table 26, 0.048 and 0.051, 0.036, 039. Longer span alpha y, that is same for any LY by LX, 0.037 and 0.028. So we have to find out for 1.25, we have to find out from the linear interpolation. So what we can get it? So we shall get the values, we shall get 4 values, 2 from here and 2 already we have got it. So these 4 values will give me the 4 moments. Okay. So shall I continue? Okay. So negative moment for LY by LX equal to 1.25 alpha x and alpha y. So, negative moment, negative coefficient and positive coefficients. We shall get it here 0.0495, 0.0375, 0.037 and 0.028. So, these are the 4 coefficients times W L square x. W is the design load. So, we shall get 4 different moments, we shall get it. You can get it from table 26. So, that table 26 you should consult. So, shorter span, support moments, (0.0495) times 12.741 times Lx4 square, which comes as 10.09 kilonewton meter. Span moment in the shorter span, we can get it 0.0375 times 12.741 times 4 square, 7.6446 kilonewton meter. What about the longer span? So, support moment, .037 times 12.741 times 4 square equals 7.5426 kilonewton meter, and span moment equals 0.028 times 12.741 times 4 square equals 5.707 kilonewton meter. So, we are getting 4 different values at different position. This is the span moment in the shorter direction, this is the corresponding support moment. Out of that we can find out 10.09 is the maximum one we are getting. So, we can start from here itself, we can find out the depth from taking this moment. So, 10.09 we can take it. So, what we can do it here then, let us find out the depth. So, maximum moment so d equal to square root of 10.09 into 10 to the power 6 by 0.138 times 20 times 1000. 1000 is the width, we are talking unit width. So, which comes as 60.46 millimeter less than 130 millimeter. So, let us complete this one, that we could find out immediately x by d 1.2 minus root over 1.44 minus 6.68 mu by FCK BD square. So, which comes as, I am not going in detail, which comes as 1.2 minus root over 1.44 minus 0.1994 equals 0.087. We are going little fast, anyway x by d equal to 0.087. Okay. So, you check these values. So, x by d 0.087. So, the next formula we shall use it as z. Z equal to d times 1 minus 0.416 x by d equals 130 times 1 minus 0.416 times 0.087 equals 125.29 mm. AST directly let us compute 10.09 into 10 to the power 6 divided by 0.87 times 415 times 125.29 equals 223.05 square millimeter. So spacing required equal to 1000 times, let us assume that 58 millimeter dia bar we shall use it because it is too less. So 223.05, which comes as 224 millimeter. So we can provide 8 torr at the rate of 200 millimeter center to center. So AST provided equal to, after computation you can find out, 250 square millimeter. So provide 8 torr at the rate of 200 millimeter center to center, that we can provide. Now similarly we can take it that directly what we shall do, now we shall not check the depth, what we shall do, because since it is checked with this maximum moment, so it will be checked, it will be true for other values. So now we can directly compute x by d, the z, and then we can provide that AST. And also we have to check that 0.12% steel, that whether it is coming more than that. If it comes that any value, because moment may be less, so in that case if it comes moment less, then what you have to do, then you have to provide the minimum reinforcement, and which is 0.12% of the that your cross sectional area. So in this case it will be area of steel minimum, that one it will be say 0.12 times 1000 times 130 shall we take, because 130 is not the 1, it could be little more also, because 131. So please note, because I have taken 10 millimeter, but now since I am providing say 8 millimeter, so it will be little more, so 1. So anyway, so whatever it is, on the basis of that we can find out the area of steel, and that area of steel always you have to check whether it is coming more than this. Otherwise, that this is the criteria of the crack width also, that crack. Okay. So we shall stop it here, and we shall in the next class we shall start with that. At least I shall give you some introduction on the concentrated load, because so far we have done on the uniformly distributed load on slabs, but I shall give you the next one, that is on the concentrated load. Okay. So thank you.